So if we look at the front of your handout, again, this is section 8.3 in your textbook. Make sure you take a look at section 8.3 in your textbook. Our electron configurations will describe the locations of electrons in an atom, and they can be determined based on the periodic table. There are two formats that we can use to write our electron configurations, and the first is the full, unabbreviated form of the electron configuration, and it looks like what we just wrote on the back side of your handout for the elements, including that of oxygen, which we see here, 1s2, 2s2, 2p4. Where in this information, that first one tells us the shell. The S then tells us the shape of the orbital or the specific subshell that we're going to be working with. And the superscript tells you the exact number of electrons that are going to be placed into that orbital. Now, we're always going to be placing electrons into orbitals from lowest energy to highest energy. And we can use the periodic table to help us make very good sense of exactly how the electrons are going to occupy the orbital. The periodic table can be broken down into the S block, the P block, the D block, and the F block. Let's start with the S block. As we look at the S block on the periodic table, that consists of group 1A and 2A on the periodic table, but also includes helium on the right side of the periodic table. Our elements in the S block are characterized by the fact that their last electron, or their highest energy electron, is placed into an s orbital. The specific s orbital where that electron is placed is equal to the period number that we have on the periodic table. So if I look at my periodic table, there are a couple of pieces of information that might help me. First, I might want to number the periods. So 1, 2, 3, 4, 5, 6, and 7. That means that I'll be placing the electrons for all of my elements across the first 7 shells of the periodic table. The elements of group 1A and 2A give rise to my S block, where all of my elements in group 1A have an electron configuration that ends in S1. All of my elements in group 2A have an electron configuration that ends in S2. The specific shell where that s orbital resides is equal to the period number. So that if I were looking at an element like magnesium, based on its position on the periodic table, I would know that for magnesium, its highest energy electron is placed into an s orbital because it's in the s block. Because it's in group 2A on the periodic table, I know that its electron configuration ends in S2. And because it's in the third period, I know that its highest energy electron is placed into a 3s orbital. So its highest energy electron sits in a 3s orbital, and that electron configuration ends in 3s2. I know all of that based on its position on the periodic table. If I were to look at an element like rubidium, based on rubidium's position on the periodic table, I know that its highest energy electron is placed into an s orbital. I know that its electron configuration ends in S1 because it is in group 1A. And because it's in the 5th period, I know specifically that its electron configuration will end in 5s1. So that for rubidium, I know that its highest energy electron, or its last electron, is placed into a 5s orbital. On the other side of the periodic table, groups 3A to 8A give rise to my P block. And so if you notice, my P block starts in the 2nd period. And what we know from our discussion of quantum numbers is that our p orbitals start in the 2nd shell. So this corresponds to where I'll be placing electrons into my 2p subshell, 3p, 4p, 5p, 6p, and 7p. So that once again, the position of the element within the p block gives me a lot of information about its electron configuration. All of the elements in group 3A correspond to where I'll be placing the first electron into the p orbital. So this is where I will start placing electrons into my 2p orbitals. All of my elements in group 3a will have an electron configuration that ends in p1. For group 4a, it's p2. For group 5a, it's p3. For group 6a, it's p4. 7a is p5. 8a, it's going to be p6. So that if I look at an element like silicon, based on silicon's position on the periodic table, I know that its highest energy electron is placed into a 3p orbital. It's in the p block, it's in the third period. I also know that because it's in group 4a, I know that its electron configuration is going to end in 3p2. If I were to look at an element like thallium, thallium is atomic number 81. It sits in the p block. Based on its position in the p block, I know that its highest energy electron is placed in a p orbital. I know that the shell where that p orbital resides is the 6th shell, and I know that its electron configuration will end in p1. So altogether, I know that thallium's electron configuration is going to end in 6p1. So based on our discussions up to this point, you should be able to write an electron configuration for all of the elements in the first 3 periods of the periodic table. If we write an electron configuration for boron, it is atomic number 5. That means that on the periodic table, we're going to start at hydrogen, which is atomic number 1, and we're going to work our way from hydrogen to helium to lithium, beryllium, and boron, and place the electrons in the orbitals indicated by the positions of those elements between hydrogen and the element that we are working toward. So the position of hydrogen tells me that the first electron goes into a 1s orbital. The position of helium tells me that the second electron also goes into a 1s orbital. The position of lithium and beryllium tell me that electrons 3 and 4 go into a 2s orbital. And the position of boron tells me that electron number 5 goes into a 2p orbital. That means that the electron configuration is going to be 1s2, 2s2, 2p1. If we add up the superscripts for that electron configuration, 2 plus 2 plus 1 is 5, which is exactly the number of electrons that we've intended to place for boron. If we look at magnesium, we already looked at magnesium in an example where we determined that based on its position on the periodic table, we know that its highest energy electron is placed in a 3s orbital. That comes from the fact that it is in the s block, and we know that it is in the third period. So if we start at hydrogen and work our way to magnesium, hydrogen and helium tell me that electrons 1 and 2 are going to go into the 1s orbital. Lithium and beryllium tell me that electrons 3 and 4 go into the 2s orbital. Boron through neon tell me that electrons 5 through 10 are going to go into the 2p orbital. Sodium and magnesium tell me that electrons 11 and 12 are going to go into the 3s orbital. So for magnesium, I'm going to have 1s2, 2s2, 2p6, 3s2. If I write an electron configuration for argon at the end of the third period, because it sits in the p block of the third period, I know that its highest energy electron is going to sit in a 3p orbital. Its position in group 8a tells me that its electron configuration is going to end in 3p6. So that if I work my way from hydrogen to argon, I'm going to end up with an electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6. And if I add up all of the superscripts, I should get 18, which means I've placed exactly 18 electrons into the lowest energy orbitals for argon. This is argon's electron configuration, but this is also consistent with how the first 18 electrons for any element that follows argon will be placed.